Emission Spectra, Part 1. An emission spectrum tells us what wavelengths are absorbed or emitted by a particular sample. In chemistry, we're often looking at tubes that hold atoms in the gaseous form. We run electricity through those atoms, and we look at the light coming out with a spectroscope or a spectrometer. A spectrometer is a device that splits light into its respective wavelengths. We see something odd when we use a spectroscope to look at emission spectra for atoms. We see that only certain wavelengths of light are emitted and others are not emitted. We know that Ernest Rutherford used a gold foil experiment to propose a new version of the atom. That atom was called the nuclear model. That model is very useful for all things nucleus. It helps us understand where the protons exist and that the atom is mostly empty space. However, this model of the atom does not answer many of the questions that scientists had at the time about electrons. One question of many is why, if protons and electrons attract, they don't collapse. If you think about it, protons being positive and electrons being negative should be things that are slamming into one another when they're in close proximity. Really, the reason why they don't slam together is electron energy. And a practical example of this is holding a baseball above the surface of the earth. When you let go of the baseball, it drops to the ground. It's attracted to the surface of the earth because of gravity. You can actually provide the baseball with enough energy to go somewhere else before it hits the surface of the earth. Obviously, when you throw a baseball, it is still dropping toward the earth, but you've given it enough energy for a second to get to where it needs to go without hitting the earth. Scientists were beginning to focus their attention on electron energy. Energy is neither created nor destroyed, just like mass. So it follows that if radiation is entering an atom, and we know that that radiation is being absorbed by electrons, electron energy must be greater. The reverse, if radiation is coming out of an atom, we know that it had to have been coming from somewhere, and we can assume that it must have been coming from the electrons. That led to a problem for scientists. When metal is hot, it glows. Glowing means that light is being emitted. If light is being emitted, a question is, where is that energy coming from? And if the energy is coming from electrons, why aren't atoms collapsing as electrons lose this energy? We have a series of laws called classical mechanics. These are laws that allow us to describe the motion of large bodies. When we drop a baseball, we can use classical mechanics to predict how long it will take to reach the surface of the earth. We found that in the case of the glowing metal, our old equations from classical mechanics weren't useful in describing what was going on. Neither was Rutherford's nuclear atom. That meant that we needed to design or theorize a new version of the atom, and we needed to do that with a new set of rules. That new set of rules is called quantum mechanics. Classical mechanics describes large bodies. Quantum mechanics describes smaller bodies. Max Planck was one of the leaders in this field. On paper, using complex mathematics, he theorized that all energy transitions must be a whole number multiple of h times nu. If the change isn't a multiple of h times nu, it's not allowed. During that time, Niels Bohr in the lab was using a spectrometer to look at emission spectra of atoms. He assumed that when he pointed the spectroscope or spectrometer at the emission spectra, that he would see a continuous spectrum. Instead, he was puzzled by the line spectra that resulted. Tune into the next video to learn about how Bohr changed our idea of the atom with this information.